Hey friends, welcome to part 2 of my video on lead acid battery sizing. In part 1 of the video, I had explained how we calculate the number of cells of a battery bank as well as the various correction factors we need to consider while sizing a lead acid battery. Link for part 1 of the video is given in the description. Let us now try to calculate the lead acid battery ampere hour capacity using the load cycle calculated in my previous video. In this connection, IEEE 485 introduces a term called period, where period is defined as a portion of the load cycle with constant load. Also for lead acid battery sizing, the duration of momentary load is considered as minimum 1 minute. By converting the momentary loads to 1 minute, the load cycle has been simplified as shown in the diagram and the load table. IEEE 485 also defines a term called section of a load cycle, where section is a portion of the duty cycle from the beginning of the cycle to the end of each period. Let us now understand the steps of battery ampere hour calculation as per IEEE 485. In the first step, we need to calculate the required ampere hour capacity of each section of the load cycle. The rate of discharge and the KT factor are taken care in this step. KT factor is a factor used to account for reduced battery capacity at higher discharge rates. Once ampere hour capacity of each section of the load cycle is calculated, then in the second step, we need to identify the maximum section capacity. This maximum section capacity is the uncorrected battery ampere hour capacity. In the final step, we need to adjust the uncorrected battery ampere hour capacity with the various correction factors like temperature correction factor, design margin, and aging margin to arrive at the required battery ampere hour capacity. Let us calculate the discharge factor KT for our load cycle. As the end of cycle voltage is 1.75 in our example, the KT factor for various durations can be identified from the battery catalog corresponding to the ECV of 1.75. Accordingly, we have KT equal to 0.45 for 1 minute, KT equal to 2.3 for 89 minutes, 3.29 for 149 minutes, and KT equal to 4.76 for a load duration of 240 minutes. We will now use the worksheet provided in IEEE 485 to calculate the battery ampere hour capacity in a step-by-step manner. In step 1, we will fill the load and the duration of each period in columns 2 and 4. Then the change in loads as the difference in current and previous period is filled in column 3. Then we fill the duration of each period from the beginning to the end of each section in column 5. The KT factor for each duration is filled in column 6. In the next step, we calculate the cell size of each period by multiplying columns 3 and 6, and the value is entered in column 7 with sign convention. The sum of capacities for all periods in a particular section is taken as the size of that section. the maximum value amongst all sections plus the random load, if any, is considered as the uncorrected size of the battery bank. Let us consider the fourth section in detail to understand how we calculate the section capacity. Loads of each period and their corresponding duration are entered in columns 2 and 4 respectively. KT factor for each duration is entered in column 6 of the IEEE 485 worksheet. Changes in load scaled by the KT factor to give the required capacity for each period within a section is entered in column 7. The section capacity is then arrived as the sum of the period capacities. Once the largest section capacity has been calculated, we can add any random load to arrive at the uncorrected battery capacity. As we do not have any random loads in our example, the uncorrected battery capacity in our example is the capacity of the fourth section, which is equal to 65.81 ampere hour. We now need to adjust this uncorrected battery capacity with correction factors for temperature, design margin, and aging factor to arrive at the required battery ampere hour capacity. Therefore, the required capacity in our example is 65.81 into 1.3 for temperature correction factor into 1.1 as design margin into 1.25 as aging factor to arrive at a required capacity of 117.63. Our lead acid battery sizing is now complete. This concludes my video on lead acid battery sizing. Thanks for watching. I hope you enjoyed this video. If you would like to see more such videos on electrical topics, please subscribe to my channel and share with your friends and colleagues. Thank you.